Right, so the next section deals with orthogonal diagonalization. Now, we've already discussed diagonalization previously, so a lot of what you're going to see in this section should be familiar. Now, if A and B are square matrices, then we say that A and B are orthogonally similar if there's an orthogonal matrix P such that P's transpose A times P is the matrix B. Now, an orthogonal matrix P is in a matrix where its transpose is its inverse. Okay, so this is similar to the definition of when two matrices are similar. They're similar when A and B are similar if I can find a matrix P such that P times A times P's inverse is B. Right, so this definition is very much similar to that previous definition. The only difference here is P is an orthogonal matrix. Okay. Right, so if A is orthogonally similar to some diagonal matrix, say D, then we say that A is orthogonally diagonalizable, and that P is orthogonally, or rather that P orthogonally diagonalizes A. Right, so if we can diagonalize the matrix A using an orthogonal matrix, then we say the matrix is orthogonally diagonalizable. Right, now, what are the conditions for a matrix to be orthogonally diagonalizable? Remember that a square matrix A is said to be symmetric if it's the same as its transpose. So that brings us to the following theorem. The following three conditions are mathematically equivalent. If A is an n by n matrix, then the following statements are mathematically equivalent. Right, so A is orthogonally diagonalizable will imply that A has an orthonormal set of n eigenvectors, and that will imply that A is symmetric. And A being symmetric will imply that A is orthogonally diagonalizable. So again, that 1 implies 2, 2 implies 3, and 3 implies 1. Okay, so those conditions are all mathematically equivalent. So again, it's if A is orthogonally diagonalizable, then we can relatively easily see that A must have an orthonormal set of n eigenvectors. Right, so let's assume that if we go back, right, so if we assume that A can be orthogonally diagonalized, then we can find a matrix P where A times P is P times D, where D is a diagonal matrix, right? And remember that the inverse of P is its transpose. Okay, so setting up that matrix equation, we can write the left-hand side as a matrix with columns, and you get the columns by multiplying the matrix A with the first column of P, say C1, multiplying the matrix A with the second column of P, say C2, and up until the last column, which is formed by multiplying A with the nth column of P. And on the right-hand side, these D's indicate the entries on the diagonal of that matrix D, and we get a matrix on the right-hand side with columns formed by taking D11 and first entry in the first row, the first column of D multiplied by the whole column, first column of P. Right, and you can then go and calculate the rest of the columns. Okay, so basically from that equation there, you can see that that part is equal to that part is equal to that part, up until there. So basically these are the C's are eigenvectors, right? So if you take the collection of these column vectors of P, that set is orthonormal, and each one of those C's is an eigenvector for all I. Why is each C an eigenvector? Each C is an eigenvector. Remember, P is invertible. So therefore, each column, none of these columns can be zero vectors. Okay, so all these columns are non-zero vectors. Okay, and therefore they are eigenvectors because they satisfy the eigenvalue equation. Okay, right. And why are they orthonormal? In other words, why are the C's pairwise orthogonal? And why do they all have norm 1? Right, so remember that P's transpose times P is the identity matrix. So how do you calculate the entry in the ith row, in the jth column of this matrix here? Is you take the ith row of P's transpose, which essentially is the ith column of P, multiplied by the jth column of P. So it's essentially, it's the ith column that you dot with the jth column of P. And because it's equal to this identity matrix, whenever the indices are not the same, it's going to be a 0. And whenever the indices are the same, it's going to be, the dot is going to be a 1. So it's going to have on the diagonal these 1s and 0s everywhere else. So that's going to imply that if you take these vectors pairwise, they are going to be orthogonal, and each one of the vectors is going to have a norm 1. So it's an orthonormal set of eigenvectors, and there are n such eigenvectors. Okay, so showing that 2 implies 3, we are not going to look at 3 implies 1. We're going to look at, let's look at 2 implies 3. So assuming that A is an orthonormal set of n eigenvectors, why does it mean that A is symmetric? Assume that A has n orthonormal eigenvectors, C1, C2 up until Cn. We can let P be the matrix formed by taking the columns. The columns to be the column vectors C1, C2 up until Cn. And also we know that Ci dot Cj is going to be 0 if I is not equal to j, and we're going to have that Ci dot Cj is going to be 1 if I is equal to j. Remember that. So this is just simply going to imply that P's transpose with P is going to be the identity matrix. Okay, and also we can set up the eigenvalue equation, which is this one here. That's going to be the diagonal with each one of these columns is going to correspond to an eigenvalue, right? So we form the diagonal matrix with the eigenvalues on the diagonal. Each one eigenvalue is going to correspond to one of these C's. Okay, and from there we're going to get that A is going to be PD P's transpose. Okay, so why is it that my matrix is symmetric, right? So that's easy to see, because from there we've got then that A's transpose is going to be PD P's transpose everything, and that is going to be okay, and that's going to be P D transpose P is transpose, and we know P is D is a symmetric matrix as well. Okay, so that implies that A is symmetrical because A's transpose is itself. Right, just some properties of symmetric matrices. If A is a symmetric matrix, then the eigenvalues of A are real numbers. We're not going to look at that. And the eigenvectors from different eigenspaces are orthogonal to one another. I just want to look at quickly at point 2, which is quite easy to see. To start off, we take two eigenvectors and let these eigenvectors correspond to distinct eigenvalues, lambda 1 and lambda 2. Basically, then, if you take the matrix A and you look at V1, we know that is lambda 1 V1, and from there, if we take that vector, and we dot it with the vector V2, that's the same as lambda 1 V1 dot V2. Okay, and writing that in matrix multiplication, dotting those two vectors is pretty much the same as saying that we're going to take the transpose of this matrix and we're going to multiply that with a matrix V2. Okay, and it's basically the same here, multiplied by that, and that is going to be V1 transpose A's transpose, which is A because A is symmetric. Okay, and that's lambda 1 V1 transpose dot V2, and basically now what you can do is you can go and replace that little part there. So you can replace it with what it's equal to, and it's equal to lambda 2 V2 because it's also an eigenvector. Alright, and from there we get that lambda 2 Vt V2 is lambda 1 V1t V2. Okay, so these are constants, and this is a vector and that's a vector, right? So the only way that equation can be satisfied, look at the right hand side and the left hand side. Okay, both the eigenvectors or both the eigenvalues are distinct, and we have we pretty much have a situation here where the only way that can be satisfied, we've basically got a scalar multiple of a vector on both sides, and these scalars are different. So the only way that can be the same is if V1's transpose is the zero vector. Sorry, not vector, is 0. And so that's going to mean that V dot V2 is going to be 0. So V1 and V2 is orthogonal. Right, so this is just a procedure for orthogonally diagonalizing a symmetric matrix. So what you do is you first work out the eigenvalues, and then you go and find a basis for each eigenspace of A, just like we did in chapter 5. Right, then remember, if a matrix is symmetric, it means it must have n, remember those equivalence conditions. We said this, a matrix is symmetrical, that is equivalent to saying that it's orthogonally diagonalizable, and that's equivalent to saying that A is an orthonormal set of n eigenvectors. So we need to construct a set of eigenvectors, n of them, and we need to make sure that they are orthonormal. We already know how to construct a we already know how to construct an orthonormal basis. And we use the Graham-Schmidt method. Right, so what we're going to do is we're going to apply the Graham-Schmidt process to each of these bases to obtain an orthonormal basis for each eigenspace. Right, so you're going to, for each eigenspace you get, remember now by the previous theorem, eigenvectors from different eigenspaces are orthogonal. So all I need to do is I just need to make sure that the basis vectors for each eigenspace amongst themselves, they are orthogonal and orthonormal, which we just get by normalizing the vector. And then once we have that, we form the matrix P, whose columns are the vectors constructed in step 2, and this matrix will orthogonally diagonalize A, and the eigenvalues of the diagonal of D will be the same order as their corresponding eigenvectors in P. Right, so perhaps it's best to just illustrate this with an example. So there's the first example. So they ask us to orthogonally diagonalize this matrix here. So that's a symmetric matrix, and all we're going to start with this by working the eigenvalues out. Right, so there we start off. We go and write the equation down. Okay, so we get the determinant of that matrix, which is lambda minus 4 squared minus plus 4, which is that. And then factorizing that, we get our characteristic equation. Setting it equal to 0 yields the eigenvalues 6 and 2 respectively. Right, then we go and find a basis for lambda equals 6. So remember what my matrix A looks like. So it's going to be, right, so it's lambda minus 4, which is 2, lambda minus 4, which is 2 there, and then the rest is there. So all minuses. And now we know what to do there. We go and look at the, we need to go and find non-trivial, well, we need to go and look at the null space of this matrix, right? We need to find a basis for the null space. So we can go and reduce that matrix to get this matrix here. That corresponds to a system, basically to this system here, x minus y is equal to 0, and pretty much y is equal to t. So therefore you set x equals to t, and so you get your set of solutions to this system here, which is going to be t. Okay, and so the basis for that is determined by the vector 1, 1. Okay, so then we look at lambda equals 2, and again that is right, so on the diagonals here you've got lambda equals 2, which is 2 minus 4, so you get minus 2 and minus 2 on the diagonal. And then again we look at the null space of that matrix, we go and reduce it to get this matrix here. And that corresponds to a system, x plus y equals 0, and we parameterize the variable y. And so your solutions pretty much become all that have the form minus t, right, and that corresponds to this basis vector. So now you've got two basis vectors, right? We've got a basis vector 1 minus 1, and we've got a basis vector 1 1. Okay, those are my two basis vectors. Now look at these two matrices. Look at these two vectors, right? Are they orthogonal? If we look at the dot product between those two vectors there, are they orthogonal? It's 1 times 1 plus 1 times minus 1, which is 0. So they're orthogonal, right? Do they form an orthonormal set? The answer is, what is the norm of this vector? Right, the norm of that vector is square root 2. Okay, and going back, what is the norm of this basis vector? It is square root 2. Okay, so those vectors are clearly not. They don't have norm 1. Okay, so we just need to change them to have norm 1. So the first column vector, which we're going to let this vector be, but I need to normalize it, so I need to divide it by the square root of 2, which is its norm. So that is going to be, of my matrix P, that's going to be my first column vector. Okay. Now, looking at the next vector, which is this one here, you need to normalize it, and so again, it's got norm square root of 2. So again, you divide it by its norm, and there you form your second column vector, and that becomes your matrix P. And again, so we can write the matrix P transpose AP as a diagonal matrix, where the diagonal matrix is formed by taking the diagonal entries to be the eigenvalues, and each one of these, the first eigenvalue corresponds to the first column of P, and the second eigenvalue corresponds to the second column of P. Right, so the next problem here is find an orthogonal matrix P that diagonalizes B, where B is the symmetric matrix. Now they're nice enough here to give us the characteristic equation, so we don't have to go and do the long work of working out or getting the characteristic equation. Alright, so there we are given B, and we're given this characteristic equation. So we set it equals to 0, and we solve the eigenvalues as 4 and 1 respectively. So now we need to find a basis for each one of the eigenspaces. So that's pretty straightforward. We take this matrix equation, and we go and look at the null space of that matrix equation. Okay. Right, so this matrix here is going to be lambda on the diagonals. It's going to be a lambda, which is 4, minus the diagonal entries. So it's going to be 4 minus 2, 4 minus 2, 4 minus 2, which is 2, and then it's going to be negative all the other entries. Alright, so looking at the null space of this matrix, it is, we can just go and reduce it to get this matrix here, and then we can go and further reduce it. Okay, and eventually we're going to get this reduced matrix. Now, if we go and look at the null space of this matrix, which is essentially, you go and solve this linear system. Basically there, you're going to set, that corresponds to the system x equals t. That corresponds to z equals t, y minus z equals to 0. And then again x minus z equals 0. Right, so that is going to yield all your solutions. And these solutions are going to be of the form, they are going to be of the form T 1, 1, 1. Okay, so the basis vector is going to be that vector there, so that's going to be the basis. Okay. Right, so now we need to go and look at the other eigenvalue, which in this case is 1. So plugging it in, we get on the diagonal, we get 1 minus 2, 1 minus 2, 1 minus 2, and negative all the other entries. And then reducing that gives us this nice little matrix. And again, that matrix, so we need to go and look at the null space of that matrix, right? So that's the same as solving that system there. And that corresponds to the system x plus y plus z equals 0. So then you can go and parameterize, z as t, you can parameterize y as s, and then you get x is minus s minus t. Right, so all your solutions become, right, so writing all your solutions down, it's a linear combination of two of those vectors. Right, so your basis becomes the collection of these two vectors. Now, we need to go and check. First of all, we know that the vectors from this basis and the vectors from that basis, they are going to, if we look at cross, well, we know from the previous theorem that those vectors are going to be orthogonal to one another from different eigenspaces, right? Right, if we take the dot product between these two vectors, right, so that's going to be minus 1 times minus 1, which is 1, plus 0. Okay, so that's clearly those vectors are not orthogonal, but we can make them orthogonal by using the Graham-Schmidt process. Okay, so we look at this basis. Right, we set the vector v1 as the first vector in the basis and v2 as the second vector in the basis, okay? And then the Graham-Schmidt method said that we create a new basis. We call the first vector v1, and we let w be the span of that first vector. Okay, and then we set the second vector as we set the second vector in our new basis as the second vector in my old basis minus this scalar multiple of the first vector, and the scalar here is the dot product of v2 with u1, and you're going to divide that by the dot product of u1 with u1, or in other words the norm of u1 squared. Now the norm of u1 squared, if we look at the dot product between u1, which in this case is that vector there, right, so if we look at the dot product between minus 1, 1, 0 and minus 1, 1, 0, okay, that is going to be that's going to be 2, right? So therefore we get 2 there, and the dot product between v2 and u1, that is going to be the dot product between these two vectors here, That's going to be minus 1 times minus 1 plus 1 times 0 plus 0 times 1, and that is going to be plus 1. Okay, so we're going to get that there. Right, so working that out, we get this vector. Okay. So the orthogonal basis, the new orthogonal basis becomes this vector here, which that's u2, and u1 is v1. Okay. Right. So that's my new orthogonal basis. And that is the base. That's the basis. That's u1, right? U2, and this is the orthogonal basis. Just say that it's the orthogonal basis for the eigenvalue for lambda equals 1. Right, so now this new basis, is it orthonormal? What does it mean for it to be orthonormal? It means each vector must have norm 1. Okay, now looking at that vector, it doesn't have norm 1. Looking at that vector, it doesn't have norm 1, but we can go and normalize it. Right, so by doing the following. Right, so we can go and normalize that. So what's the norm of a u1? What's the norm of u1? The norm of u1, it's going to be the square root of, we said u1 is that vector, so it's minus 1 squared plus 1 squared plus 0. And that is going to be the square root of 2. Right, so if we look at u, divided by the norm of u1, it is going to be the new vector. It's going to be minus 1 over square root 2, 1 over square root 2, 0. Okay, and the norm of u2 is going to be the square root of, it's going to be the square root of minus a half squared plus minus a half squared plus 1, which is going to be, it is going to be a quarter plus 1. And that's going to be square root 3 over 2. Right, we can just get rid of that square root in the denominator, and that you can just write as square root 3 times square root 2 divided by square root 2 times square root 2, and that is just equal to square root 6 over 2. Okay. Right, so normalizing u2, that's going to be so you're going to divide that by the norm, and that's going to be the vector minus 1 over square root 6 minus 1 over square root 6, 2 over square root 6. Right, so my orthonormal basis for lambda equals 1 is therefore going to be the matrix, or rather the first vector. There's my first vector, and the second vector is going to be that vector there. Okay, there's my orthonormal basis. Okay, Right, so now having normalized those two vectors, then I form a matrix P, where P is now my column vectors. And the second and the third column is going to be formed by those two vectors, and the first column comes from my first eigenvalue basis, right? That was my first eigenvalue basis. I need to normalize that vector. So what is the norm of this vector? What is that vector normalized? The norm of that vector is the square root of 3, right? So it's 1 over square root 3, 1 over square root 3, and that is going to be the vector in my first column, which is that vector there. Right, so that's your matrix that's going to diagonalize your given matrix B. Right, next up we've just got a little concept called the spectral decomposition. If A is a symmetric matrix that is orthogonally diagonalized by this matrix P, remember now these vectors are n eigenvectors that are orthonormal, and if those eigenvectors correspond to these eigenvalues, then you can express A as a sum between column vectors, a linear combination between column vectors, right? So, and that is called the spectral decomposition of A. Right, so look at this example here. They ask us find the spectral decomposition of these two matrices. We already calculated for both these matrices in the previous example. We calculated the eigenvalues and the matrices P that form part of diagonalizing them. Alright, so this is a straightforward example to do. Let's look at A, the first one. Now recall that for A we calculated the eigenvalues as 6 and 2 respectively, and we calculated the first, the eigenvector corresponding, or the unit eigenvector corresponding to 6, we calculated it as that vector there. Remember, if we go back there, this matrix P we calculated for that matrix A, we calculated it as P has the first column, which is that matrix, and the second column, which is that matrix there, multiplied with that scalar. Recall that this column corresponds to the eigenvalue 2, and that column corresponds to the eigenvalue 6. Alright, so that is the eigenvalue, unit eigenvector corresponding to 6, and that was the unit eigenvector corresponding to 2. Right, and then it just involves plugging it in. This is first vector transpose multiplied by the same vector, and that's the second vector transpose multiplied by that vector there. And simplifying, we get that A can be expressed as a sum, scalar multiple of 2 by 2 matrices. Right, then if we go back to B, remember we calculated the eigenvalues of B as 4 and 1 respectively. For the eigenvalue 1, we had 2 vectors corresponding to that eigenvalue. And remember we got those 2 vectors. We got this unit vector, the vector we obtained by normalizing the old basis vectors. Right, and then we have the first column vector, which corresponded to the eigenvalue 4. And then it's just plugging it in. We've got the first column vector transpose, multiply a dot with the first column vector. Then we've got the second column vector transpose, multiplied by the second column vector, and take note of the eigenvalue there, which is 1. Okay, and then we add the third column vector corresponding to the eigenvalue 1, which we take the transpose and multiply it with that vector there, and then summing that together, we get that we can express B as a sum between 3 by 3 matrices. Right, so that's called the spectral decomposition of